Okay, good afternoon, everybody. I'd like to introduce Marcello Margioni from CodePlay, who will talk to us about predication and vector code generation.
Hi, everybody. I'm Marcello Margioni from a company called CodePlay, and we work a lot with GPUs in general and problems like vectorized code over multiple SIMD units. And so I'm here to present like a technique that could be implemented through LLVM, like also see how to implement it through LLVM, and an overview of what I'm going to talk about is this. So we will have like a little introduction about data parallel languages, SIMD architectures, and how to fit these two together. And then we'll look like in detail, in certain level of detail, how to implement this approach that I will present in the second part, which is the implementation part. So data parallel languages. These are some of the most famous, OpenCL, CUDA, and RenderScript. They're becoming increasingly popular these days, even if they existed since quite some time. And they're at the characteristic of you take a program and you run it over a lot of threads. Is the same program, but you run it on a different data set. So each instance of the program actually runs on different data. By the fact that these many threads actually run the same code, this paradigm is kind of friendly to SIMD architectures. So it's very interesting actually to try to exploit this fact on SIMD architectures, because SIMD architectures are kind of becoming pretty popular today and common. Like every CPU or has some kind of SIMD capabilities, and most of GPUs are structured in an SIMD way. They're quite efficient in running data parallel flow if the control flow is uniform and doesn't actually diverge. And these kind of architectures actually reduce the flexibility of the architecture itself in order to be able to pack more processing unit inside the core. So you basically have a core that has more processing units, but these units are not as flexible, so you cannot diverge their control flow arbitrarily. And this is one of the problems that you encounter when you want to merge these two approaches. These two things, SIMD and data parallel applications. And this is the approach like we want to achieve, like having a single SIMD processor and running a thread for every processing unit of this SIMD processor. So we want basically to have, like, if we have four, in this case, let's say 4 OpenCL threads, we want to run each thread on each different processing unit of the SIMD processor. And the main problem you encounter with this is that when divergent branching happens, so that when these threads want to diverge, you basically need to handle it in some special way, because SIMD units cannot diverge. They share the same program counter usually, so they need to execute the same instruction, and so you need to handle that specially. Our approach is like we get the IR, which is scalar, okay, and then we lower it by auto-vectorizing basically every instruction over the entire SIMD width. And then we linearize the CFG by going from this kind of form to this. And what we want to do is basically making sure that the semantic of the program is maintained by masking out the side effects of instruction that shouldn't be executed. So basically, we run all these basic blocks in a sequence, but whenever a basic block shouldn't be executed because a condition actually decides so, we basically mask out the side effects that the instruction can have, like writing registers or accessing memory, etc. So basically what we want to do is this. So at the beginning, all these SIMD processors are running this entry basic block. And then when actually half of the processing units in this case want to follow the then branch and the other half want to follow the else branch. So what we do is basically disabling while we execute the else branch half of the processing units and do the opposite then, and then we merge back into the end. There are two kinds of approaches that you can use. One is an IR approach, which actually has been also presented in previous presentation in an LLVM conference from Ralph Karrenberg, for example, that applies this kind of thing on CPUs, and by using selects and using those kind of instructions at IR level. IR level doesn't have support for predication, so you cannot like mask out effects of instruction easily that have side effects like a store. If you store somewhere, you cannot like say do that only if that certain predicate is true. You need to be able to handle that differently, so you may need some kind of special handling, scalarization, whatever. Another kind of approaches are backend approaches, where you do implement that in the backend, and this can make use of all the hardware because you have access to whatever you want. You do what you want. And hardware predication can be exploited because you can define instructions that have predicates at the backend level. So actually, the approach I will introduce is more this kind of the backend because we want to use predication. What is predication? So predication is a kind of hardware feature, basically disables the execution of instructions if a certain predicate is false. So like this is an example, we have these comparisons that we have two kind of registers in this architecture they made up to make the example. We have two kinds of registers, normal registers, which are like vector registers in this case, and mask registers. So this comparison writes the result of this comparison into this mask register, which basically is like the predicate if the comparison was true or false. Then we have this instruction called setMask, which loads the mask into the hardware, okay? And from that point on, every instruction that is predicated is executed following the condition of the mask. So this other instruction, which is add VP, which is not it's a vector add with predicated. The P should be stand for predication. Is only executed and the result is stored into R0 only if the predicate is true. So. First step, how do we predicate instructions in LLVM? Basically, the approach that is used is mainly by adding an extra operand at the table gen representation of the instruction. And this operand basically specifies the predicate of the instruction. So you might have, like, I don't know, an instruction, you don't want the instruction to be predicated, you set the operand to 0, I don't know. And you want that instruction to be predicated, and you set it to 1. And this predicate operand, when it gets selected, the instruction from IR into the actual machine instruction, it usually generates a default predicate value, which usually is always execute. So don't predicate because the IR is not predicated, so that's the default thing. So this is an example from the ARM backend. This instruction, LDR post, has this pred extra operand, which is actually the predicate. And the spread operand class is defined in another file, which has this form. It inherits from predicate operand, which is an LLVM predicate class. And here there's the definition of the operand is two 32-bit immediates, and this is the default value of the operand. 14 stands for always execute, which means do not predicate. And this is other stuff that is needed for backend implementation. If you are interested more into like how to implement backends, there's a talk tomorrow about that. And yeah, this is basically how to predicate an instruction. You simply add an extra operand to an instruction, and that's done. So now, to actually achieve what we want, there are some steps that you need to do. And the first one that you should do is like determining an execution schedule for your linearization of the basic blocks. So basically here we have an example. We have this diamond that gets translated into this, and the order is specified in this way by the colors, you see. And what is a valid schedule for linearization? A valid schedule is a schedule where a basic block is scheduled after all its predecessors, basically. So yeah, how do you find such a schedule in an LLVM? One way is by doing a reverse post-order traversal of the CFG, which is a kind of traversal of the graph, where you basically visit first all the children, let's say, and then the father, and then you reverse that order that you find. Luckily, LLVM has a easy way to do it. You can use the reverse post-order iterator, which is an iterator you can apply over a machine function, and it automatically gives you this order. So you can use that in order to get this order. Another way of determining the instruction schedule is by using this relatively new pass that came out in LLVM called structurized CFG, which is used actually by other backends like the AMD R600 backend for their Southern Island GPUs. That basically structurize the CFG for you. So if you have like an unstructured CFG, it structurizes it. And also by doing that, because it is not simply structurizing it, but it's transforming the IR in a very specific way, it also generates a valid execution schedule for the basic block. This is what it does. So we have a simple code here, which is just an if with an or condition in the middle, and generates this unstructured control flow here. And the pass actually generates this, which has some more basic blocks, but it changes the code in a way that might actually simplify a lot of the subsequent passes, depending also on your architecture, depends. And this is another example, like when we have a structure instead control flow. This control flow is structured, but still it modifies it in a way that, as you can see, it basically introduces linearization of the basic blocks in advance. So it does that for you. This might have advantages and disadvantages from point of view of performance, but it depends. So the next thing you want to do is allocating the execution masks for your basic blocks, which means that what you should do is like associate to each basic block like a mask, which basically tells you, oh, I want to execute this or not. And if the mask is true, the basic block should be executed. And if the mask is false, instead it should be disabled. Disable the side effects. And each mask is basically a value. So it needs to be stored somewhere, and then you need to retrieve it at the right moment in order to load it when the execution of the basic block starts. And the life, basically, of the mask is defined. It starts from the predecessor. The predecessor defines the mask for the successor. So this should execute or this should execute. And this value should be alive until it's consumed from the basic block that needs to run. And in this case, we have that these two set the flag for this. Actually, in this case, the M0 mask is reused here because this dies here, so we can use it back for this. So we can also do some smart allocation. How do we allocate those masks inside LLVM? Well, we have two approaches. One, we can use like LLVM virtual registers. So we have virtual registers, and we simply set the masks as virtual registers, and we use one register per mask. Or we do some kind of custom allocation. The one register per mask approach is okay if your architecture has specific predicate registers, but you need to, in order to be consistent, because actually I forgot to say one thing. The linearization of the CFG in this approach happens after register allocation. So if you use virtual registers for mask registers, you might have a problem that the register allocation does an inconsistent register allocation over the registers, so that some registers overlap and they write to the same physical register and it doesn't work. If you run the structurized CFG pass over the code before before doing the register allocation, actually that fixes up the code in a way that you're sure that the register allocation is consistent, which is good. But you need to run the structurized CFG pass. The custom mask allocation instead permits you to not run that if you don't want, so you can deal with any kind of unstructured control flow. But it needs you need more work, because you need to allocate the resources manually, and depending on the architecture, you might be able to be more optimal. Because, for example, in other architectures, you might be able to store more masks into a single register because maybe you don't have access to specific predicate registers. So you need maybe to store this into other registers. And so you can avoid wasting registers if that is the case. But you also you cannot use the register allocator, so the spilling infrastructure of LLVM. So you need actually to really do this, saving the registers and loading them back yourself. Yes. So after you allocated these resources, you need to insert code inside your function in order to handle this. So this is the kind of code you might want to insert. An example of code from the previous CFG, like that we have the diamond, BB0, BB1, BB2, and BB3, those if-else diamond. And here we have like that there is this comparison which generates the mask for BB1. And then we generate the mask by simply inverting it for BB2. And in BB2, we need to insert this code that loads the mask and sets the mask for BB3. And the same for BB2. Load the mask of BB2 and set the flag for BB3, which is ORing its own mask into BB3. And then BB3, of course, also has the loading. So you need to insert this code by simply inserting instructions at the right points, like at the beginning of the basic block or after comparison that is used originally by the branch that jumps here or here. And after many trials, what we found is that it's better doing that after register allocation. The reason for that is that LLVM makes some assumptions during register allocation and just before register allocation, where the spiller can insert code everywhere in the middle of your instruction sequences, and also file elimination doesn't make a lot of some assumptions. So it might screw up your code if you don't pay attention. So doing that after register allocation is better. Then we have next steps, which are this CFG linearization phase, which is very simple actually, because you already determine like the order of execution of all your basic blocks, and you simply reorder them in the order you meant at the beginning, and connect all the successors in a line and remove all the branches instruction that have been selected and from IR. And you keep only the packages in order to implement loops. So you have to have loops, you need to keep the packages. And the next phase, easy phase, is actually predication of the actual instruction. So you might have this is not needed to be late on in the pipeline, but can be also early on. We basically change the predicate. The predicate has been default selected as always execute from the instruction selection phase. And in this phase, you just change the predicate of all the instructions that are not mask handling instruction from always to follow the predicate, basically. It's just a switch, change the operand inside the machine instruction, and that's it. Yeah. So optimizations for this. At the moment, I just explained an approach that basically linearizes the entire CFG. You might don't want to do that, because if you're able to avoid full linearization, you're actually saving a lot of execution of code that shouldn't be executed. So if all the units want to jump to a certain specific basic block, you don't need to run the one that nobody wants to run. Okay? So the main optimization approach for this is to avoid linearization. And there are two ways of doing that. You can have a static approach, where you do some kind of analysis, and a runtime approach, where you basically check at runtime if the condition, if the unit split or diverged or not. So the static optimization, you need some kind of analysis that actually analyzes your jumps, your divergence, and determines, okay, this jump is uniform for all the units. It will never diverge. And it's simpler to do if the CFG is structurized, because this analysis is easier. There are papers on analysis like this, and these analyses are easier if your CFG is structured. Simple as that. And if the analysis is successful, you can actually avoid completely like allocating masks. You can avoid inserting extra instructions for mask handling, etc. But it might miss some cases. So as every static optimization, it might miss some stuff. Runtime approaches instead are more complete in the sense that they always catch all the cases. Sometimes are quite easy to add to your implementation because the hardware actually is thought with that in mind. But they don't. You still need to put there all the flag handling, flag allocation code, because you want to be sure that if the runtime optimization doesn't catch the case because they diverge, the unit diverge, then the infrastructure for managing the masks and loading them must be there. But catches more cases, not potentially, actually, this is wrong. Catches all the cases. So this is an example of a runtime optimization. The red is not the best color, but basically we have the code from before that is completely linearized. And here simply we add this J O Z jump, which basically means this all Z means jump if all the unit have the mask to 0. So if no unit actually wants to run BB1, jump to BB2. And we skip here the code of the else branch, and we go directly here if that is the case, basically. And this is an example. So I want to talk also a little bit about the advantages of this approach with respect to more IR-based approach. So because we are doing the linearization after register allocation, one of the advantages is that we lower the register pressure. And the reason for that is that if we linearize the CFG beforehand, basically the register allocator of LLVM says, oh wait, these base blocks are running in a line. So the live ranges of registers are actually overlap, no? So I cannot allocate the same registers for these two instructions. And in this way, LLVM emits more registers than needed. But because we are masking out the execution of the basic blocks, disabling actually the writing to registers or to memory with predication, actually that is not needed. That safety is not needed. So we can, by doing the linearization after register allocation, LLVM thinks, oh, this is a normal CFG, so I just allocate the registers as usual. And basically we have the maximum, the lowest register threshold that is possible. And this optimization is quite easy actually to implement inside the LLVM, because you have access to all the other features, and you're in a backend which is kind of free. And it's actually quite, because you don't need to tweak the register location because you're doing this trick, and there are actually quite few passes to run. And in a very specific phases, you don't need to tweak a lot of LLVM. And this is good because LLVM changes a lot and very quickly. So if you need to change it deeply, if then you want to follow tip, you might need to rewrite a lot of stuff. So this approach actually we found out that is very good for following LLVM tip. So this is a summary of what I talked about. A little bit of an introduction on data parallel languages and assignment architectures. And then I try to explain a little bit on how this approach works and how to implement the various steps that you need to do inside of LLVM, like determining execution schedule, adding mask handling instructions, allocating the execution masks, linearization, the optimization you can do, and what are the general advantages. And if you have any question, please ask. And these are my contacts. Thanks.
Do you have any plans to mix into this work a predicate analyzer?
Predicate analyzer.
Yeah, so you can in principle, so you have all these predicate expressions, logic expressions, which determine which portions of code run. It is possible to determine algebraic relationships between these results, between these values, like equivalency, implication, and mutual exclusivity. These are the primary free ones. These free relationships actually can be used to change the nature of the interference graph of a register allocator. So you can actually tell the register allocator that actually certain things don't conflict and other things should conflict. And the reason that you said the LLVM's allocator trashes the code unless you are linearizing the graph in a certain way is probably this one. If you are able to do predicate analysis, extract this information, and then feed it into the register allocator, then one, you should get minimal number of registers, and two, you should get correct allocation without having to restrict graph linearization to a very particular strategy.
That is actually a very interesting approach, yeah. At the moment, I mean, like in LVM, there is the R600 backend, which is the other backend that does this, apart from the one we work on, maybe in Coldplay. But there's another backend that work with this approach, and they actually use the structurized CFG pass. But I mean, that is something that can be done in order to avoid maybe to run that pass, which is kind of sometimes not optimal. Yeah.
Is anyone able to comment on how much upheaval that might be to the register allocator? There are register allocation experts in the house. Do you have a view, Michal?
At least for a linear scan or a greedy register allocator, basically you have to rewrite it. If you had a graph coloring allocator, then it will be a matter of removing edges and adding edges, and it's simple. If you're using an integral linear programming allocator, then again, it should be simply a matter of changing a bit the matrix. So if you're not using the fast greedy one, you should be okay, in principle.
But that requires to change the register allocator some way.
So no, if you had a graph coloring one,
okay,
then you could just build your interference graph and then take in your predicate analysis output and just change a few edges here and there. With a greedy one, you have to rewrite it. With the ILP one, I'm not sure, but I suspect it could be adapted easily.
Yeah, so I see what you mean. Yeah. With the default one of LLVM at the moment, I don't think that is possible without touching it.
So I know nothing about LLVM's register allocator, but I can confirm that in principle it would be easy in a coloring allocator, but the devil is in the detail. Questions?
Hi there. Is there any hardware features that make predication easier, or things you'd like to see, basically? Hardware features.
Well, it depends heavily on what you already have. Like, typically, I mean, everything I saw of the other hardwares that I had my eyes on, I don't know if my boat about what I already saw, so I'm kind of used to that, and I feel like it's fine. But if I see that now there's a lot of this trying to put this like in new architectures, like I don't know, Intel Gen GPUs, where they try to actually do this kind of thing, like to disable automatically the lanes without having to insert any code at all. In that case, that might be useful. Okay, of course, would make maybe this talk a little bit less, a little bit more pointless. But if you have an hardware feature like that basically by checking the program counter, you basically set, I want to run this program counter, so enable the units only if I'm jumping to there. If I want to jump somewhere else, disable me. That is a feature that Intel has that I think which is pretty cool. So something like that. Yeah.
Okay. Right, thanks.
So I noticed you had stateful setting of the predicate bits in the hardware.
Mm-hmm.
So some instruction sets actually have the predicate register as part of the instruction. Mm-hmm. Would that make life easier for you?
Well, you wouldn't need to set the mask at the beginning. You would still need to use it throughout the entire basic block, basically. Yeah. I don't know if it would make the life easier, because at a certain point you need to, maybe you want to reuse the registers for a later basic block because you want to save it. No? So if you're doing the location manually, then you have less. Maybe you can put that instruction that sets the next predicate register everywhere inside the basic block that does the setting. If you have an hardware predicate register, because you simply load it and then boom, that register is free. If the mask needs to be used by every instruction, you need to put the set for the next basic block that wants to use that register in a certain specific point of the basic block, where basically all the instruction use that and you don't need it anymore. But
questions? It's always someone a long way away.
So your runtime optimization kind of works because you can assume data locality in the languages you're sort of translating into the system, right? Are there any optimizations apart from that you can imagine could help if you could say like 95% of the time I take the same branch anyway across MD lanes?
Well, I guess well, because I haven't thought about that, so I don't know. But I mean, I guess that you still need to execute both, right? Even if you do that optimization, you're skipping entirely the branch that basically don't need to be run, right? But if you even one unit needs to execute the other one, no? Mm. You need to execute both.
Yeah, but sometimes at runtime you can detect all of them are following the same branch, and maybe you could like clone a function that can assume it's all there.
Yeah, but if you do the runtime optimization, you don't know until the comparison is run. Like maybe the approach you mean is like combining of an analysis pass and...
Yeah, at compile time you can clone the functions and then at runtime specifically go into a specialized function. I just wondered if you had
but
done
what
it.
if there are like divergence inside the function that you're calling?
That's the interesting bit, yeah. Sorry, the tricky bit.
Okay. I cannot think at the moment. So, yeah,
okay.
Needs more.
Thank you. Any further questions?
Not much walking this time. Say you have not one condition but two. You have two flags, and then you typically get that code. If flag 1 is set, then if flag 2 is set, then do this, else do that, else if flag 2 is set, else do that.
You mean if conditions with multiple,
right,
something like that?
And you immediately see that first you have code duplication because you need to do the check on the second thing twice, and second you have alternatives. You can check for the second flag before, or check for the second flag first or the first flag first. And I'm fairly sure different alternatives will give you different code after you serialize it. And maybe it's worth looking into just finding those patterns and looking at all those other ways to write those patterns and serializing them and seeing if some of those are better. Have you tried that?
Yeah, that would be interesting. See, having like multiple, you mean like having, like making specialized paths in the case of multiple conditions are true, something like that, or no?
Not quite.
No, maybe I haven't got what you said.
You have two flags, which can be true or false. So you have
But
four
we are
cases.
talking about the if, like the code level, or we are talking about the like flags like masks and a point of view of the hardware, like the predication.
Both. On the code level, you have the ifs. On the instruction level, you have the masks. And if you switch around the ifs on the code level, you most likely get different flag instruction code. I mean, set masked instruction code.
But these ifs are like one nested inside the other, or are the same condition of the same if? Right.
Nested ifs.
Okay. Yeah, it's basically what we do is like working from the IR. Okay, so you get the IR, which has been translated by Clang in a certain way from code, and then you work with that. So we don't think about the ifs at eye level with this approach. But certainly, I mean, I guess if you put something further up in the chain that maybe optimizes more the IR that arrives to you, you could certainly like get better results in the end, like having more optimized code that, I don't know, some stuff is merged or the CFG arrives in a form which is more easy to handle and generates less code, extra code. So,
Doesn't that make it unstructured?
well, it could be. Depends on what you're doing. But this approach actually is able to handle a structured control flow. If you don't have the register allocation, if you do the register allocation yourself or use the approach that has been proposed previously.
So, according to my watch, it's time for tea. I think that clock's a little bit pessimistic, perhaps. It's still stuck at breakfast time. Can we thank Marcello in the traditional way, please?